All right, so this is example number 1 for rotational inertia. So it's a lot of information for not a very difficult problem. And I just turned it upside down for myself. There we go. Large machine components that undergo prolonged high-speed rotation are first examined for the possibility of failure in a spin test system. In this system, a component is spun up or brought to a high speed while inside a cylindrical arrangement of lead bricks and containment liner, all within a steel shell that is closed by a lid clamped into place. If the rotation causes the component to shatter, the soft lead bricks are supposed to catch the pieces for later analysis. In 1985, Test Devices Incorporated was spin testing a sample of a solid steel rotor, which they tell us is a disc, which is important here, of mass m is equal to 272 kilograms and radius r is equal to 38 centimeters. When the sample reached an angular speed omega of 14,000 revolutions per minute, the test engineers heard a dull thump from the test system, which was located 1 floor down and 1 room over from them. Investigating, they found that the lead bricks had been thrown out into the hallway leading to the test room. A door to the room had been hurled into the adjacent parking lot. 1 lead brick had shot from the test site through the wall of a neighbor's kitchen. What? The structural beams of the test building had been damaged. The concrete floor beneath the spin chamber had been shoved downward by about 0.5 centimeters, and the 900 kilogram lid had been blown upward through the ceiling and had then crashed back into the testing equipment. The exploding pieces had not penetrated the room of the test engineers only by luck. How much energy was released in the explosion of the rotor? This is a true story, and there's a picture of what happened of like the wreckage in your book, and this is in chapter 10, of course. So if you want to see that picture, check out in your book in chapter 10. So first and foremost, let's just write down our givens. And again, physics problems sometimes, especially your book, they like to give you a lot of information, but only some of it is relevant. So the relevant information here is that the mass of the disc, I just put mass and disc together in my head for some reason, is 272 kilograms. The radius is 0.38 meters, because it says 38 centimeters. Of course, I just converted straight to meters. And then it says we reach an angular speed omega of 14,000 revolutions per minute. So our angular speed was 14,000 revolutions per minute, which of course we want in radians per second. So I'm going to convert that right away. In 1 revolution, there's 2 pi radians. And in 1 minute, there are 60 seconds. So our omega ends up being 14,000 times 2 times pi divided by 60, which is 1,466 radians per second. Now we want to know how much energy was released. So here we know when it was spinning at really high speed, it had a lot of kinetic energy, and that's the energy that's going to be released. So kinetic energy we know is 1/2 I omega squared. I as in rotational inertia, omega as in angular velocity. So remember, we're spinning here. We're not translating. So it's not 1/2 mv squared here. It's 1/2 times rotational inertia times angular velocity squared, I omega squared. So of course, the reason that the disk information that I underlined here is important is because that gives us the rotational inertia equation that we're going to use here. So kinetic energy is equal to 1/2 times our rotational inertia, which in this case of a disk, it's 1/2 mr squared times omega squared. Okay, now 1/2 times 1/2, of course, is 1/4. So we get kinetic energy is equal to 1/4 times m times r squared times omega squared. Here we can just plug in our numbers. We get kinetic energy is equal to 1/4 times the mass, which was 272 kilograms, times our radius, 0.38 meters squared, times omega, squared. So I'm going to square this omega times 0.38 squared times 272 times 0.25. And we end up getting a really big number. Kinetic energy is equal to 2.11 times 10 to the 1, 2, 3, 4, 5, 6, 7th power joules, of course. So that's our answer. That's how much energy that thing had and then is released when the whole thing exploded.